So good morning, everyone. So I'm Sougata Mukherjea. So I will talk about network visualization for the next 2 days. So visualization is a subject by itself. So I teach a course on visualization in IIT, but today our focus would be only on network visualization. So what we will do first, we will give an introduction to what is visualization. So many of you know about visualization in Excel. You can do bar graphs, pie charts, and also those are also some form of visualization. But our focus is on graph visualization. I will say about graph visualization, and one of the main challenges of graph visualization is graph layout. I will talk about that. And then we will talk about tree visualization. Trees, as you know, is a uh, kind of graphs, a simplified form of graph. And then we will talk about interaction, how you interact with graphs, because unless you can interact with the visualization, you cannot understand it well. And then finally, we will talk about some network visualization software. We will have some hands-on session on that. Okay, so stop me anytime if you have any question, so that we can have a interactive class. So what is visualization? So the purpose of visualization is to convey information to people through graphical representation of data. Okay, so you can have, so nowadays you have a plethora of information explosion. So you can get lot of data. So sometimes if you can see a visualization of that, if you can see some patterns, that will help you to understand the data better. Okay, so it has been defined as formation of visual images, the act of or process of interpreting in visual terms or putting in visual form. And so most recently, a definition has been added, a tool for method for interpreting image data fed into a computer and for generating images for complex multidimensional data set. Okay, so you have lot of data, multidimensional data. Graph is one form of that, and you want to create some images out of that so that you can understand it better. Okay, so it's a kind of cognitive process where you form a mental image of the data so that you can understand the data better. Okay, so it has also been called as the computer supported interactive visual representation of data. But visualization is not new. So from days immemorial, it has been utilized. So for example, it has been used for maps, for scientific drawings. So maps you can consider to be a form of visualization of the spatial data. And so for thousands of years, people have been using maps. There have been scientific drawings that has been used for a long time. And so most of the concepts learned in devising these images carry on straightforward manner to computer visualization. And so the basic of that has been computer graphics. So computer graphics has been used to study various kind of scientific processes, and so you can have computer graphics to look into models of molecules, and also those are kind of visualization also. But what we focus on is, of course, information visualization and specifically graph. Okay, and now with advance in computer hardware, you can create visualizations on the fly, interact with that, and so on. So what we do in visualization, we have some reality, like the reality can be some graphical data. So what we do, we have a computer representation of the data. So that data may be nodes and link kind of diagram that we have. And then we create pictures of that. The viewers can look into the pictures, and that gives them a understanding of the reality, and then maybe they will do some interaction, change the computer representation in some way so that they can get details. So if the visualization is very big, they may do some filtering to remove some part and get that part in better detail. Okay, so visualization is really about external cognition. That is how resources outside the mind can be used to boost the cognitive capabilities of the mind. Okay. So what you want to do in visualization, you firstly want to record some information. So you can record, in our case, it would be information about graphs. Then you analyze the data to support some reasoning tasks. So, for example, you have some hypothesis of the data, or you want to find out something about the graph. What are the main elements of the graph? Find some patterns in the data. So you analyze the data and you then present that information so that you can communicate that better to others. And as I said, visualization has been going on from thousands of years. So, for example, this is a map of some town in Turkey that was drawn on the walls in the caves. And then Galileo had created some visualization about the phases of the moon. So these are recording some information that is there in reality. You want to show it in pictures. Okay. Then you can also analyze the data. So for example, this is a planetary movement diagram or the wind map. So you can look into this data to understand it better. And then also visualization is useful to communicate some information. So this has been recognized as one of the best visualizations that was created, and still it shows some of the great features of a good visualization. So this was created by someone called Jacques Minard in 1812, and it shows how Napoleon had invaded Russia. So if you see at the top, it shows the number of people that was there, number of French army that was there. So the size shows that a lot of army people were there going for the invasion, and as they were coming back, the soldiers were dying because of the war or because of some diseases on the way and so on. So a good visualization can, just looking into the view, you can get a lot of information that is not possible just by textual description. However, visualization is not good for every use cases. So for example, if you exactly know what you want, you can just go to Google or search it, or now you can go to ChatGPT to get more information. But visualization is useful for more exploratory. You have given a data set, you want to understand what data set is about. You don't have any exact knowledge of what you are looking for. You want to just understand the data better. You don't have some prior question. You don't know. You just want to look into the data to ask what questions you want. If you already know what you want to do, you can do search. Search is much better. And browsing is another way of is also used as contemporary to visualization for looking for interesting something in the data. Okay, so visuals can frequently take place of many words, and you can summarize the data better. But sometimes you also need words besides the visual pictures. So for example, you may want to have labels in the graph. So what are the challenges in visualization? So if you are told to do a visualization of the graph, so first you have to decide how you will show the data. What is, you have been given a graph of something, how you visually represent the data. Do you do it by node and link diagram, or you do it by some other method? So you have to decide on that. And the main challenge is the scale of data. So for example, if you have to visualize a large social network, though, the amount of data that you have, you cannot show it on just one page. So what are the things you can do to visualize large amount of data? That is a challenge. And then also there is diversity of data. In this course, we are only looking into graphs, but in other places, there are other things that you want to visualize, like table data, or you want to visualize textual data. So there can be diversity in the data. That is also a challenge that you have. So how is the information visualization done? So you have some raw data, so this may be some graphs. From there you create some data tables. The data tables may be the nodes and link diagram. And from there, from the data table, which is textual, you form some visual structures. That may be a node and link diagram, and then you create some views which you show to the user. the user has some task in mind. He wants to use the data to understand the data better or find some patterns in the data and so on. And so the user can interact with the visualization. They can change the view that is given. They may not like it, they want to do something else, so they can change the view. They can change the visual mapping. So for example, in the visualization, suppose you have used the color to represent gender, so maybe they want to change the visual mapping, they want to use something else for the color, and they may want to use some shape for something. And they may transform the data also. For example, if you have a large graph, you may filter it out some part and show just part of the data for the visualization. Okay. And so what S. Few, who is another noted researcher in this field, had said, the effectiveness of information visualization hinges on two things: the ability to clearly and articulately represent information, and our ability to interact with it to figure out what the information means. So the first part is creating from the raw data, creating visualization, and then how you interact with the data so that you can really understand the data better. So both are very important for information visualization. And how generally information visualization works? It does not work by itself. You have the process called visual analytics, where you analyze the data using visualization, but you also have other things to that. For example, you may have data mining to that. You may have some complex kind of textual representation of some part of the data. So visual analytics is the whole field that is there. So you have visualization, you have computation and analysis, you have analytical reasoning, and that is what helps in the overall process of understanding the data. Okay. So this gives a short introduction to visualization. So now we will focus on graph visualization. So graph visualization is a similar thing. You have some graph data. You create some graphical representation of the data using visualization techniques. And the user has you show the visualization to the user. The user has some goals or tasks, and they will interact with the visualization to understand that better so that they can answer the questions that they have. So what you have to do in graph visualization is to decide on the representation, on what type of way do you want to visualize the graph, and also how you can interact with the visualization. So we will look into various ways you can interact with the visualization. Okay. So you can have different tasks or goals that you want to use the visualization for, and that can be attribute-based task or topology-based task. Attribute-based tasks are tasks that are related to some attributes of the nodes or some attributes of the links that you want to find out, while topology-based tasks are tasks that are related to the graph structure. So how is the graph structure forming? What are the different shortest path and things like that. So the task can be of three types. One is localized, so find a single or multiple nodes edges that fulfill a given property. So for example, in attributes-based task, you can find edges with the maximum edge weight, while in a topology-based task, you find all adjacent nodes of a given node. So in attribute-based task, you are looking for attributes of a particular node or link, while in topology-based task, you are looking into the graph structure. You can also try to quantify, count or estimate a numerical property of the graph. Okay, give a number. For example, in attribute-based task, you can say give the number of all the nodes, how many nodes are there. And in topology-based task, you can say give the in degree of a node. Okay, and in sort and order, you can enumerate the nodes and edges according to a criteria. So, for example, sort edges according to their weight, or you traverse a graph starting from a given node. Okay, so there can be different types of tasks, and for that visualization can be utilized. And you can either have it based on the attributes or the topology of the graph. Okay. So Ben Schneiderman, he is a well-known scientist in this field of visualization. He's from the University of Maryland. So he came up with some of the criteria of what is a good graph visualization. So what he said was every node should be visible. For every node you can count its degree. Okay. For every link you can follow from source to destination, and you can see patterns. So for example, clusters of nodes or some nodes that are outliers, you should be able to see them. So these are some of the things that you need to do when you create a visualization. So for example, this is a good visualization. Okay, this is a visualization of a social network, and all of the attributes that Ben Schneiderman mentioned is there. You can see every node for, so the second one is every node you can count its degree, so you can count the degree of every node. Then also what you can see is for every link, you can see from which source to which destination the link is going. And also that is one key thing. So the first three things you can do in just if you take just list the nodes on the links. But the last thing, finding clusters, finding outliers, those things only a good visualization can do. So for example, in this visualization we can see some groups of people are forming, and this kind of things can be shown only in a good visualization. You can see the different groups that are forming with just because you have done a good visualization of the data. Okay. So we had talked about challenges of information visualization. Graph visualization has some of those challenges. So first challenge in graph visualization is the graph layout. So for example, here we had laid out the graph in such a way that the clusters were easy to form. So how do you form this kind of layout? So what are the algorithm that you will use for that? Okay. So graph layout and positioning, this is a big problem. So people have been studying this problem for multiple years. So there have been a lot of research papers written on this, how you lay out a graph. So second one is navigation interaction. So how do you interact with the graph? So especially if the graph is large, how do you interact with the graph so that you can see patterns of data forming? And of course the scale is a big challenge. So if it is a small graph, then the first two can be done. So there were a lot of graph algorithms that work well for maybe up till 1,000 nodes, but after that it does not work well. So if this graph is really huge, both these are big problems. So the layout and the interaction. Okay. So these are some of the major challenges that we will see what people have done so far to solve these problems. And but there are still a lot of open areas, so these problems have not been solved efficiently so far. Okay, and you can see that we showed a good graph layout, and this is a bad graph layout. Okay, so it is, so if the number of nodes increases, it is not easy to visualize a large graph. So all the things that Schneiderman had mentioned, none of the things are applicable for this. We see here that a lot of the nodes are not visible. For the links, you cannot see from which node to which node the links are going, and this is just a tangled mess. So what we call a hairball visualization. So what it does, it just shows a lot of clumps of data, so you cannot make head and tail out of the data. So this is not a good way to visualize graphs. Okay, and most of the times if you have a large number of nodes, a lot of the graph visualization algorithms will come up with this kind of views. So how do you visualize the nodes and the links? So that is the first simple task that we have. And of course, we can have the nodes represented as squares or circle, links represented by lines, and then you can create a visualization of that. So this is the most common way of representing a graph, and you can have a free visualization, or you can have it styled. You can put it in a grid and show the visualization. And of course, if there is a fixed embedding. So for example, if your graph is representing a geographical area, for example, it is representing all the cities of India, then the position of the nodes is predetermined. You have to put them in the places of where the actual city, put it in an India map and put the nodes in where the cities are. So there it's fixed, so you don't have to do much. Okay. So how can you represent the nodes and links? The simple way is using a node and link diagram, and then you can use various attributes. So for example, so for each of the node is just not the node position, nodes have information. So for example, if it's a social network kind of graph, then the nodes represent various people. If it is a telecom network, the nodes will represent, for example, phone numbers, and then each of the nodes will have some attributes. So for example, if it's a social network graph, the nodes will represent people. The people will have their gender, they will have their age. So you can use various node attributes like shape, color, size, and of course the label to map those. Similarly, the links, you can use the color to represent various types of different types of links. The thickness can show the weight of the edge, and so you can utilize various kind of visual attributes also to augment your visualization. Okay. So now you have the nodes and the links, and so what you now need to do is to lay it out in a graph. Okay. And so what are some of the criteria for good node link layout? You want to minimize the edge crossings, you minimize distance of neighboring nodes, you minimize the drawing area. So if you, of course, if you have an infinite drawing area, you can draw a really large graph, but you want to show it in a small space. So for example, you want to show the visualization so that it can be shown in a laptop display, and now also in a mobile display. Can you show a visualization in a small area? Okay. Then you want to have uniform edge length. So you don't want some edges to be really big, some edges to be small, and so on. Okay. And aspect, so these are some criteria that are good to have, like aspect ratio about 1. You do not want a really long visualization where the length is very high but the height is not very high. And another key thing is the symmetry. Okay, so suppose two graphs are almost similar, they may be differing in 1 or 2 edges or nodes, then they should look similar when you use an algorithm to lay them out. So these are some of the criteria for a good node link layout. So what are the criteria and justification for that? You want to minimize edge crossings because that improves the readability and aids the user in following paths. Okay, if there are edge crossing, then as the edges are crossing, the user mentally gets confused. So if the edges are not crossing, it's easy to follow from where to where the edge is going. The symmetry aids in understanding of the structure of the graph. If two graphs have very similar structure, their visualization should also look the same. Okay. Uniform edge lengths for a regular structure that prevents graph becoming distorted. So you want to have the edge lengths to be similar. One edge length should not be very big, another should not be very small. So also you want to have uniform node distribution so that the visualization looks better. And so you also want to have non-adjacent node separates. If two nodes are not connected by links, they should not be together. If nodes are connected by links, they should be together. And so also the node edge overlap, nodes and edge should not go over a node, because then what happens, it can look very clustered. So these are some of the criteria for good node link representation, but obviously it is not possible to map everything together. So for example, you are saying that you want to avoid edge crossing, and you are also telling that you want to have uniform edge lengths. So those are conflicting criteria. If you have uniform edge lengths, then there would be some edge crossing. Then you are telling the space should be utilized better, and then you are also saying that it should be symmetrical. Okay, so those are conflicting criteria. So So therefore, that's why graph layout becomes a challenge, because there are a lot of criteria for a good layout, and those are conflicting criteria. So therefore, it is not easy to do that. Also, two other criteria that are important in the days of where you want a computer algorithm to produce the graph layout. First is predictability. Okay, what does predictability means? That suppose you have a graph algorithm that given a graph produces a layout of the graph. What you want is if the algorithm is running twice, both time it should produce the same layout. It should not be that the first time it produces a layout and the second time it produces a totally different layout. Because then what happens is it becomes difficult. Each time you run the algorithm, if you get a totally different layout, it would be very confusing for the user. And also time complexity. You want the graph layout algorithm to ideally be real time. You want it to the algorithm to be given a graph, and in real time it should produce the layout. So those are also two important criteria that you have for graph layout. So now take a piece of paper and for 2 minutes try to see if we talked about adjacency matrix in the last lecture, so you know what is an adjacency matrix. So these are just 9 nodes in the graph, and they have connected by edges. So to just understand how difficult the problem it is, try to see whether you can by hand create a good layout for this graph. So we talked about a lot of criteria for graph layout. So if you want to keep all those criteria in mind, can you use this 9 nodes which are connected by links and create a good layout? So one of the criteria that we talked about was edge crossing. So this is an interesting criteria we have, right? So what we are telling is that you do not want to have edges crossing in the layout. But you can see here we have multiple cases where edges are crossing. And so what is the thing is that there are graphs where edges will cross if you want to draw it in a plane. Okay? It is not possible to avoid edge crossing in some graphs. So planar graph is a graph that can be drawn in a plane without crossing. Okay? So it's but a non-planar graph is that you cannot have a graph drawn in a plane without edge crossing. A plane graph is a planar graph with a fixed embedding. So for example, this is a planar graph which has a one embedding as a fixed graph. So this is the same graph, another embedding of the same graph in a plane. Okay? Okay, and this one is the same graph where it is not a plane graph. Planar graph but not a plane graph because you have drawn it with edge crossing. So these are the smallest non-planar graph. So these graphs, whatever you try, you cannot draw it without edge crossing. K5, K33. So these graphs, however you try it, you cannot draw it without edge crossing. So what is K5? K5 is 5 nodes in a graph where all the nodes are connected with each other. Now the second exercise for you. Try to draw K4 without edge crossing. So suppose you have 4 nodes, and if you want to try to draw it without edge crossing, what you need to do is to have 3 nodes as a triangle, as I said, and the 4th node has to be in the center. Then you can draw it without edge crossing. Otherwise, you cannot draw it without edge crossing. Smallest in the sense the number of nodes and the number of edges. Okay. If you add nodes, then it will become bigger. So can you think of a non-planar graph which are smaller than this in the terms of number of nodes?
Any non-planar graph will have at least these as their subgraphs.
Yeah, exactly. So that is one algorithm we'll talk about. So what I mean by smallest in the sense the number of nodes and the edges. So if you have any non-planar graph, this will have these as subgraphs. You cannot have a graph without this. Okay. And as he said that this is an algorithm which can be used for planarity testing. So what it says is a graph is planar if and only if it does not contain K5 or K33 as a minor. Okay, a graph H is a minor of a graph G if H can be obtained from G by a series of 0 or more deletions of edges, deletions of vertices, and concatenation of edges. So if you have a non-planar graph, it will have this K5 or K33 as a minor. So if you can draw a smaller graph than this which is non-planar, then let me know. So these are the smallest non-planar graph. Okay. So this planarity finding is a very simple algorithm. It can be done in order n time. Okay. So we have looked into what is the problem of graph layout, why is it difficult, and from the 70s till now, people have come up with various algorithms for graph layout, trying to see how you can have all those criteria that I talked about, the aesthetic criteria. You try to avoid, you try to minimize edge crossing, you try to do it in a smallest area, you try to have uniform edge length. So a lot of technique, a lot of aesthetic criteria are there. So people have been trying to create various kind of graph layout algorithms. So we will now look into those. Okay. So we talked about planar drawings. So of course we want planar drawings. You do not want, because you want to draw it in a sheet of paper or you want to present it in a computer screen. But obviously you won't be able to do it all the time, especially if the graph is already non-planar. Okay. So this is for this simple graph, you can definitely draw it like this with no edge crossing. But generally what happens is it is better to show it aesthetically. If you have a straight line, then it's much more pleasing. It looks better. So you would like to do it in straight line. Okay. So every planar graph has a plane embedding where each edge is a straight line. So obviously it cannot be that you have a planar graph, you cannot draw it without straight lines. There would be some embedding where it would be straight lines. Okay. So how did this field of, so we talk about graph visualization in the context of social media, we talk in context of protein-protein interaction network. But how this graph layout problem started was much before this. It started for circuit design. When you design a circuit, you are given a grid like this, and then you have various kind of circuit elements, and you have to put it in this grid so that in an efficient way, so that you can have smaller and smaller circuit. So the problem of graph layout started in the 1970s. So there is a conference for graph drawing that started in the 1970s, and it initially started with grid layout, where you have a grid which is a electric kind of circuit, and you have various kind of circuit element. You want to put it in this grid so that it can be, you don't want to create a very big grid. You want to have a small grid which has all the circuit elements, all the connections between them, and so on. So vertices are points in a plane on a grid, and edges are polyline. Okay, so this was grid layout that was initially done. And the objective of this was to minimize the grid size. Okay. Obviously, as I said before, that if the nodes and the links are representing a geographical area, then it's very easy to draw the graph because the node position has to be fixed. So this is a geography-based layout of the underground railway system in Atlanta. Another kind of visualization that you can have is called circular layout, where you lay out all the nodes as edges on the circumference of a circle, and the edges will be connecting the nodes. Okay, so this is called a circular layout. So here the node position are understandable, but the edges, if there are a lot of edges, the diagram becomes very difficult to understand. And later on, we will look into techniques to simplify this kind of circular layout. So one of the first popular layout algorithms that was created was called Sugiyama layout, which is a kind of hierarchical layout. Obviously, we will talk about trees later on. So trees are can be formed for graphs, so without cycles. So they tried to, from the graph, they tried to impose a hierarchy on the graph. And so how you can impose the hierarchy? If you can remove the cycles in the graph. So they tried to create a hierarchical layout. If there were cycles, they tried to remove those cycles and introduce some dummy nodes if required. And they tried to put the nodes in a layers. Okay, and they tried to have a left to right kind of arrangement of the nodes to minimize the edge crossing. So this algorithm was quite popular initially, but obviously for a small graph you can try to have this kind of hierarchy imposed, but for large graphs this is not possible. So one kind of algorithm became very popular for graph layout, which is called force directed layout. So what it tries to do was to so this kind of algorithm has become very popular. Still people are trying to create versions of that. So here they tried to model a graph as a physical system. Okay, so here what happens is the nodes are generally some physical objects who are attracted to so for example you can consider the nodes to be springs, and if there are two nodes which are connected by springs, what they will try to do is to come close to each other. And also so there is an attractive force between the nodes. Also you can model the nodes as charged particles. So if the charges are the same, what happens? Two charged particles repel each other. So there are two forces acting on the nodes. One is an attractive force if the nodes are connected by edges, and there is a repulsive force if the nodes are not connected by edges. Okay? And so what happens by this is that nodes that are connected by edges will try to come close to each other. Nodes that are not connected by edges will try to repel each other. And that way, maybe if you can simulate a physical system and try to minimize the total number of forces, then you will get a good layout. So based on this principle, lot of algorithms has been developed. Okay. So the first one was done by a guy called Peter Aids, I think. So in this paper, in 1984, this is the basis of all force-directed techniques. So the nodes are modeled as steel rings and edges as spring. Okay. So what happens is that the system is put into some random initial configuration and released, leaving the system to reach a stable state. So what happens is that so the nodes are connected by edges by the springs. You know, in physics there is something called the Hooke's law. So the springs, what they do is that they try to come close to each other. So the nodes will have attractive force, which is given by C1 by log D by C2. And there is also a repulsive force. So the nodes are also repelling each other. So if they come close to each other, they will start repelling each other. So where C1, C2, C3 are all different constant, and D is the distance between the nodes. So this was the first kind of force-directed layout algorithm developed by Ease, and so it showed some good results. So for example, if you have a graph like this, you can, as it runs through, you can get things like this. So you can avoid edge crossings, a lot of the things. So this algorithm became popular, and then other people also. So this is the spring embedder for a protein-protein interaction network with 283 nodes and 1749 edges. Okay. so this AIDS algorithm became very popular, and then Fruchterman and Reingold, he also uses similar kind of algorithm. So all this algorithm has this principle that they will have, so nodes will have a attractive force and a repulsive force, and then they have some other things to create a better layout. So in Fruchterman and Reingold, what happens? Vectors are connected by an edge, should be drawn near each other but not too close. Layout should have an even node distribution, few edge crossing, uniform edge length, symmetry, and fitting the drawing the frame. Okay. Here also there is an attractive force and a repulsive force. Okay. Attractive force is d square by k, while repulsive force in coin is k square by d. Okay. Also, they introduced another parameter called k, which is the optimal distance between vertices. Okay, so you want to have the vertices at the optimal distance, and that distance is determined by the area. So if you have a large area to draw the graph, then you can make it higher, but if you have a smaller area to draw the graph, then that k should be lower. So you want the nodes to be close to each other. Okay. So Fruchterman Reingold also added another parameter called the global temperature. So if it is hot, nodes move further each step, and if it is cold, it's smaller movement. So when you start the algorithm, you have it hot, the global temperature is high. So then the nodes, because then the graph is totally random. So initially you want the nodes to move far distance so that you can come up with the optimal layout. But generally, as the nodes are coming out to their optimal layout, you reduce the temperature so that the nodes do a little movement. So the node may be already almost in its place. So you just move it a little so that it adjusts a little to create a better layout. Okay. So as the layout becomes better, the amount of adjustment becomes finer and finer. Okay. So that is what is Fruchterman-Reingold algorithm. And this, but the one problem with this algorithm, it's not guaranteed to converge. You start and then it will move on. Each step you try to move the nodes closer so that they come to a better place, and you try to reduce the overall force, but it will not converge. So after about maybe 100 or 1000 iteration, you have to stop. Okay. But overall, this algorithm is easy to write. So you have the area of the graph, which is the width into length. Then you have the graph, then you have the area of the graph, which is the k parameter. Then you have the force of attraction and the force of repulsion. And then for each of the step, you try to move the nodes a little so that you can have a better layout position of the nodes. Okay. And so that's how this algorithm works. So this is the same protein-protein interaction network using Fruchterman-Reingold algorithm. So this energy-based approaches, so they have considered the layout to be a minima of an optimization problem where the energy function encodes the desired properties of the graph. So you can consider this force-directed layout to be a optimization problem. What is the optimization problem? That you try to have a function that you are trying to optimize, which you are trying to minimize or maximize based on various criteria. So all this energy function, what it does, it tries to create an energy function based on all the aesthetic criteria. So for example, the number of edge crossing, the distance between the nodes, and so on. And so what it tries to do is then that I try to optimize that algorithm so that the overall energy of the graph comes down. Okay. So the algorithm, initially it will focus on the speed until the nodes are comes to their almost stable position. Then you try to have precision. And this algorithm force atlas. So you will, in the afternoon we will talk about Gephi. So in the Gephi, all these algorithms, Fruchterman, Reingold, force at last, these are all given in the Gephi tool. Okay. So you can have various options that can be configured in the force at last tool. Okay. So the force at last algorithm for the protein-protein interaction network. So what are the advantages and disadvantages of the force-directed layouts? Okay. So there is strong theoretical foundation. So these are based on physics model like the spring algorithm or the charge particle. So all those have physical foundation. So there's a strong theoretical foundation. And as I said, most of those algorithms, there are few lines of code. I showed you the code for Fruchterman, Reingold. And so it has good, writing those algorithms is not very difficult. But nowadays you will have all these algorithms in like Gephi tool that we talked about or NetworkX library that we will talk about. They have all these algorithms already as part of those libraries. So you don't have to write them by hand. So till about 1,000 nodes they will give good results. And they works well in structures such as grid trees and sparse graph rather than the dense structure. If a graph have few number of edges, then these nodes will work well because the algorithm is dependent on both the number of nodes and links. Okay, so but that disadvantage is they are computationally expensive and often produces poor layout for large graphs. So different algorithms have different time complexity, but overall their order is order v square plus e. Okay. For interactive visualization, limit is about 1,000 nodes. Okay. So till 1,000 nodes they will work well. So you know what is the complexity of algorithm? I think. Okay. So these algorithms also, one disadvantage of these force directed layouts are these algorithms are not predictable. So I talked about predictability, right? That if the same algorithm is run twice, they should produce the same result. But these force-directed layouts are not predictable. So why do you think they are not predictable?
They depend on initial conditions.
Yeah. So they depend on initially you just have a random layout of the graph. Okay, so you have a random layout of the graph and then the forces start interacting with each other and then try to create a good layout. So what happens for each running of the algorithm, because of the random layout, initially the nodes are in different position and how the nodes will interact, you cannot foresee that this node is interacting with this node. So therefore, each time you run the algorithm, the visualization would be totally different. Okay. But still, this is one of the best ways to create a visualization. Okay. So people have, of course, worked on how to improve this. And so one of the, as I said, that one of the problems with these algorithms is that these are take a long time. So one technique people have tried is multi-level techniques. Find a sequence of coarser representation of the graph. The coarser representation are created by collapsing connected nodes whose edges become the union of all the edges. So suppose you have a 1,000 node graph, okay? So you from there you collapse nodes that have a lot of edges connecting them. It's kind of like clustering the nodes. Okay, so you try to cluster the nodes together, and by that clustering, maybe you will get from 1,000 nodes, you will get a graph of 100 nodes, and from there, and then you try to run the layout on that 100 node graph, and then put the layout back into the original graph. So that is one way to do it, and so an example is if and who. So this also is an algorithm you will see in Gephi. Okay. So what does the if-and-who algorithm does? So if more than 50% of those, so you try to collapse the edges together. So you try to collapse the edges together if they have connected to a lot of nodes. If more than 50% of the nodes remain after the edge collapsing, then the algorithm uses the maximum independent vertex sets, MIVS, for their coarsening procedure. So the independent vertex set is formed if there are no two nodes connected by an edge in the subset. Okay, so for that they use something called the Burns-Hart approximation. So what does the Burns-Hart approximation do? So they place a square over the initial layout of the graph and they divide into 4 parts. Okay, if there are more than one node inside each subsquare, they then divide it to 4 more again. So I want to show it. So suppose you have a layout with so what this Burns-Hart approximation does, it tries to divide this area into 4. Okay, and then they try to continue dividing the area. If there are more, if there is one node, they will keep this area. If there is more than one node, anyway, so you got the idea. So they will divide the area into 4, and each of the time, if that area has only one node, they will keep it. If there are more than one nodes, they will start dividing the area again. So that way what happens is that you create a structure like a quad tree where each root node has 4 children, and then they will try to cluster those children together and create a graph like this. Okay, so this way what happens, you have a coarsening of the graph. You start with a graph which has a very few nodes where at the high level, and then you try to go on increasing the complexity of the graph based on the clusters. So this is an example of the Ifan-Hu algorithm where initially this is the most coarse kind of graph which you try to visualize, and then what you do is that once you have created a good visualization coarse graph, you try to go into each of the clusters and try to visualize those again. In this way what happens, you start with a small graph which is at a high level, and then you go deeper and deeper into this. Okay, so this algorithm has done better job in create for large graphs. Okay, another technique that is used a lot in not only in visualization but in other areas also, for example in machine learning, is dimensionality reduction. So what is a dimension of data?
Number of different aspects.
Different aspects of the data. Yeah. So for example, if you have a table with 10 rows, you can say that that is 10 dimension. So what you try to do in dimensionality reduction, you can start with the 10 dimension, you try to reduce the dimension. So go on reducing the dimension till you come to 2 on 3 dimension, and then you can do some calculation on those 3 dimensions. So how you try to do this dimension reduction is just not random. What you try to do is that obviously if you are moving from 10 dimension to 8 dimension to 6 dimension, in each of this reduction you are losing some information. But what you try to do is that when you lose that information, you try to lose it such a way that the amount of information loss is the smallest. Okay? So you try to, so for example, from 10 dimension, if you try to go to 2 dimension, you try to do it in such a way so that the amount of information lost is the smallest. So in a graph, or what you try to do is that when you reduce from a high dimension to low dimension, you try to do whether some measure that was there in the high dimension is maintained when you are there in the low dimension. So for example, if you are trying to do dimensional reduction for a graph layout, you may try to do it so that if 2 nodes were close to each other in a higher dimension, when they come to a lower dimension also, they have that same kind of graph theoretic distances. The 2 common techniques for dimension reduction is PCA and multidimensional scaling, and both of them have been used for graph layout. Okay, so it's a technique. So as I said, what it tries to do is that when you try to move from a higher dimension to a lower dimension, you try to make sure that the lower dimension are the principal components that capture most of the variance of the data. So you are trying to move from suppose you have data about a cancer patient, which has lot of fields about the age of the patient, what is the size of the cancer. So if you have a huge dimension data, if you want to commit to a lower dimension, when we are talking about the tools, I will show a example of that. You want to have the principal component that captures most of the variance of the data. Okay, and PCA has been used for graph layout. So what they try to do in this high dimensional embedding is to follow the conveyor of placing adjacent nodes close together and not adjacent nodes far apart. Okay, the graph is first embedded in a high dimensional space by choosing 50 nodes as pivots and associating each pivot with a dimension. So now you have a 50 dimension data. Okay, the nodes are then expressed so that the graph theoretic distances between the nodes are maintained, and then you reduce the graph to a 2-dimension space using PCA. Okay, and while you are doing the PCA, what you try to do, you try to have the least variation in the data. So this way of doing the graph layout has been found to be very fast. So this is one of the quickest layout technique that is available.
So can you please repeat how that was done?
So you understand PCA? You understand? Okay. So what they do is that given the graph, they will choose 50 nodes. So suppose a graph is very large. So they will choose 50 nodes as the pivot. So the 50 nodes are representing all the nodes. Okay. And then they will try to do is that so 50 nodes is 50 dimension of the graph. From there they will try to reduce it to 2 dimension using PCA. Okay, and then they will see the position of the nodes using those PCA. So how those nodes will be positioned, and then from there they will now do a coarsening kind of algorithm, so that you can, from each of those, you can try to see what will the clusters form for those nodes. Okay, so that is how they do this. So MDS is another nonlinear technique for embedding data in a low dimensional space. And so what it tries to do in this case, it's not trying to get the principal components, but they are trying to have a pairwise distance between the nodes kept mapped from the high dimension to the low dimension. And this can be done for the graph also. So here what you have some nodes as pivots like the previous case. And then what you try to do, you try to do a multidimensional scaling and come to a lower dimension, keeping the graph theoretic distances to be the same. Okay, and the pivot nodes are high dimension nodes, which you then try to expand and get all the nodes in the graph. Okay, so these is dimension reduction techniques have been a new kind of techniques that have been used and has to be found to be pretty useful. Okay. Amit, how long can I go?
Yeah, 15 more minutes.
15 minutes. So another technique, so we have looked into graph layout kind of technique. Another technique that has been used, which is totally different. So far we have just looked into the node and link diagram for creating the layout. Another technique what has been used is using the node attributes for the layout. Okay, so for example, if can we create a visualization using the node values. Okay, so for example, we can use the node attributes to impose some restrictions on the placement of the node. We can use the node attributes as a member of a group of cluster, or directly map an attribute or attributes to a coordinate in the layout space. So let us look into some example. So this is a pivot graph. So what they try to do is to cluster on some common node attributes, put all the A's together, all the B's together, and so on. Okay. So here what happens in this example, what they did, communication network of people in a large company. X dimension is the division, Y dimension is the office geography. So all nodes that are from a particular division, they are grouped together. All nodes that are from a particular region, maybe from north or from the east, they are also grouped together. And so that way they create a graph where the focus is on the different divisions and the different geographies. And if there are links between nodes in those geography, then you connect the links between them. Okay? So this is one way of showing. So it focuses on the two variables. So the problem with this kind of visualization is you are now showing only two variables and you don't support continuous variables. So you are just looking into two variables and trying to create a visualization on that. So another visualization where again it's a graph visualization but they look into the attribute is a paper by Schneiderman and Harris. So here these are cases about US courts, okay, legal cases in US courts. So some of the cases are from Supreme Court and some of the cases are from the Circuit Court. And what happens in legal cases is you can form a graph structure because each case will refer to a previous case. They will say that, okay, I am creating this judgment based on a previous judgment that has been done. Okay, so what they did is they grouped the nodes based to region. So for example, all the cases in the Supreme Court are shown together, all the cases in Circuit Court are shown separately. And also then the position of the nodes are not based on any link layout kind of algorithm, but they are first grouped based on the court where the cases were, and then they are grouped based on the year of the case. So for example, if a case is 82 or 84, they will be put into that area. So it's kind of putting the cases in a scatter plot diagram. So all the Circuit Court cases are put in a scatter plot diagram and all the Supreme Court cases are put in a scatter plot diagram. And then how do they show the links? So for example, if you click on a node and then you can see all the links that are there. So this court case has cited all these other cases. If you click on a node, you can see all the links of the case. So this is completely a new way of showing the visualization where you are focusing on the node attributes and not on the link structure. Okay. Also what people have done is that people have, instead of node link diagram, they have used the adjacency matrix and created visualization based on that. So given the node link diagram, you can talk about the adjacency matrix and show the adjacency matrix instead of the node link diagram. Okay. So these are examples of visualizing a graph using the adjacency matrix. Okay. You can understand how these matrices are formed. So for example, X is connected to all these nodes. So we have a path to all these nodes. So what are the advantages and disadvantages of adjacency matrix based visualization? The advantage is that if you want to see the neighbors, it's very easy to do in adjacency matrix diagram. So what are the neighbors of B? It is very easy to see that you just look into that particular row and you can see that B is connected to A, C and D. Okay, but they are not suited for path related tasks. So for example, if you have to say what is the is there a path from A to B, so from the adjacency matrix it is not easy to do that. Okay, and so this is one visualization which is a hybrid of matrix and node link. So what they do is that they show the larger part they know the node link diagram, but if you focus deep into one part of the graph, they show a matrix visualization to see the details.